Over the past couple of days, we've been talking about how to solve linear equations. We looked at 2 lessons ago, reminding us what we learned in Algebra 1 about how we can use our distributive property and subtract from both sides and multiply and divide and add on both sides. Yesterday, we looked at what to do when there's more than one variable in there. Today, we're going to look at linear inequalities. So we're going to go back to having just one variable in here. But instead of being an equal sign, it's going to be some sort of a not equal comparison. So a linear inequality should have just that one variable to the 1 power, so just to the first power. A solution is something that makes it true. But in an inequality, typically we have a range of solutions that are going to make it true. So what we're going to do is graph our solutions on a number line to show which part of the number line would work to make our statement true. To solve a linear inequality, we can add, subtract, multiply, and divide just like it's an equation. Except if we multiply or divide by a negative, then we need to flip around the sign. Right? So in division, that would be that the negative is on the bottom of the fraction. In multiplying, it'd be that number that we're multiplying both sides by. Okay? Whatever we're applying to both sides, if that number is negative when we multiply or divide, we need to flip around our arrow. When we graph our solutions, we're going to use an open circle if there's not an equal to bar underneath our greater than or less than. We'll use a closed or shaded in circle if there is an equal to bar underneath that symbol. So let's see what these would look like when we actually go to solve. Okay, so first thing we would do to solve if this were an equation would be what? Add 8 to both sides. So 5y less than 20. You can add and subtract just like it's an equation. We don't have to be careful at all with adding and subtracting. Then how would I get y alone? Divide by 5. Now this is where we have to be careful and ask ourselves, was I working with a negative? The 5 is positive, so this is okay. If we multiply or divide by a negative, we need to flip around that arrow. In this case, we don't, because 5 was positive. So this is our solution. Then we want to graph that solution on a number line. So I'm going to make a number line. I always put 0 on my number line, and then the number that our answer is concerned with, so in this case 4. Now what y is less than 4 means is that y can get really, really, really close to being 4 as long as it's smaller, but like 3.99 is still okay. It just can't be 4. So we use an open circle to say I can't quite get to 4, but I can get really close. And I want everything that's smaller than 4. So we shade in that side of the number line. You can check your answer by taking something that's shaded in and plugging it in, and it should make a true statement. So if I would plug 0 into the original problem, I would get 0 minus 8, or negative 8, is less than 12. Yeah, that's true. Negative 8 is less than 12. If I would plug in something that's not shaded, like a 5, I should get a false statement. So if I plugged in a 5, I would get 25 minus 8, which is 17. That's not less than 12, so that's a false statement. So that helps me confirm that my answer is right. Questions? Go ahead and try this one. Okay, so the first thing I would do in this problem is add 9 to both sides. Adding, we don't really have to be careful about, just making sure that we do it to both sides, but we don't need to be careful with our sign. Then to get the y alone, I'm going to divide by 11. This is where we need to be a little bit careful and make sure that the number we're working with on both sides is a positive number. So 11 is positive, we don't have a problem, so I get y is greater than 2. That's our solution. Then we want to graph that solution, 0, 2. Open circle, because there's no equal to bar, it can't actually be 2, it can just get really close. Y is greater than 2 means I want the numbers bigger than 2.
Can we use like a highlighter?
Yep, highlighters would be good, or colored pencils, or you can just kind of darken them in like I do. Alright. This one has variables on both sides. So you have some choices. And there are two main ways you could do this problem. Each of them kind of has a pro and a con. Okay? So I'm going to show this problem both ways, and then you can kind of choose which way you think is going to be better for you. They're both completely valid, and they both have a benefit and kind of a downside. So the first way of solving this one is when we had equations that had variables on both sides, I said my preference is usually to keep the variable as a positive value. So what I would do on this one as an equation is begin by subtracting 2x from both sides. So that gives me a 1 less than or equal 4x minus 1. Then I would add 1 to both sides. Adding and subtracting, we don't have to worry about that sign. And then I go to dividing. I'm dividing by a positive 4, so this is not a problem. And I get 1/2 less than x. So that is one way of solving this problem. Another way of solving this problem is to always move your variables to the left. So I would then begin by subtracting 6x. That would give me negative 4x plus 1 is less than or equal to negative 1. Then I'm going to subtract 1. Negative 4x is less than or equal to negative 2. Then I'm going to divide, and this is where you have to be careful. I'm dividing by a negative 4. That's a negative that's happening to both sides of this problem, so the arrow has to flip. And this would be our solution. It's the same exact solution. So each of these I said has a pro and a con. To me, the first way of doing it, the one that I did in purple, the benefit of it is you probably won't lose negatives. Negatives are really easy to lose. They're kind of little, and sometimes they disappear in a problem. So the benefit of doing it the first way and always moving your variable so it's positive is you don't have to worry about losing a negative. Okay? The downside of this first one is when it comes to graphing, it takes a little bit more thought sometimes because that arrow doesn't necessarily show you which way to shade. So I have to think to myself when I go to graph that, which numbers is this really talking about? So I'm going to put a 0, I'm going to put a half, I'm going to put a closed circle because it has that equal to bar, and then I have to ask myself, what is this really saying? A half is smaller than x. If a half is smaller than x, then that means x is actually bigger than the half. So I would shade this way. With the second way that I did it, the way in green, the benefit is when you get to your answer, that arrow is going to point you in the direction of the shading. If your variable's on the left-hand side, your arrow tells you which way to shade. The downside is you might lose a negative along the way, and you might forget to flip your sign. Okay? So each side kind of has some goods and some bads about it. So what you have to decide is, where am I most likely to make a mistake? And try to choose the way that will help you not make that mistake. If you feel like forgetting to flip the sign or losing negatives is going to be your biggest problem, then you're probably going to want to do it the purple way. If you feel like putting it onto a graph and shading in the right way is going to be your biggest problem, then you're going to want to do it the green way, because that way it'll show you which way to shade it. So it's a preference thing, totally up to you, both ways are completely valid.
Do we flip the sign when you divide by a negative, or just?
Divide or multiply by a negative, we need to flip the sign. Yep. Okay? So go ahead and try this one. This one has variables on both sides again as well. So this is where you have your preference of which way you want to do it. So whichever way you feel more inclined, go ahead and try this one out. Okay, so my preference is keeping variables positive. So I'm going to subtract 7x from both sides. Then I'm going to add 12 to both sides. And then I'm going to divide by 3 on both sides. And since I kept my variable positive, I don't have to worry about flipping around my sign because I'm dividing by a positive number. If you do it the other way, you may have had to flip your sign. So this is what I get to. You can turn this whole thing backwards if that helps you graph and just kind of read it backwards, making sure the arrow is still pointing towards the same thing. This says the same thing as x is less than 7. And that might help you graph because now that arrow points in our direction of graphing. We need the equal to bar, so we need the closed circle, and the numbers less than 7 are to the left. Questions? Those last inequalities are what we call simple inequalities. Don't be like, oh man, those were hard and those are the simple ones. Simple doesn't mean easy. It just meant there was only one to deal with, only one greater than or less than sign in the problem. Compound inequalities are when we have more than one greater than or less than symbol in the problem. There's 2 different ways we can do that, an and or an or. An and will be one string together. It'll all be in one piece. And when we graph it, it's going to have endpoints. So to use a geometry term, it's going to be a segment. Okay. An or will be in 2 separate pieces. It'll look like 2 completely separate problems, but we're going to graph them together. And it's going to have an empty middle in the graph and have 2, using again a geometry term, 2 rays that point away from each other. So this is an and problem. It's all together in one piece. Our goal is to get the t alone, just as it always is. But whatever I do to one part, I must do to all 3 parts. So I'm going to add 8 in the middle to get the t alone, but I then need to do that to the left and to the right as well, on each side of an inequality symbol. So that gives me 6. It's less than or equal to 3t. It's less than or equal to 18. Then I'm going to divide by 3 to all parts. That's a positive 3 that I'm dividing by, so I don't have to worry about flipping any signs. If I were dividing by a negative here, I would need to flip all of the signs. So this whole thing would be turning backwards if I was dividing by a negative. You get 2 is less than or equal to t, less than or equal to 6. And that's my answer. We could read this as saying t is between 2 and 6. So then graphically, that's what we want. Equal to bars mean that I shade. Here they were the same. They don't have to be. One could have an equal to and one could not. So pay attention to that. It's okay to have one closed circle and one open circle. Then our answer is the numbers that are between 2 and 6. Questions? Try this one. Okay, so this one's pretty quick. There's only one thing to do to get the t alone. T is being added to a 4, so we need to subtract a 4 from all parts. So it's going to give me negative 13, less than t, oops, not less than or equal, just less than 6. So to graph, we put a negative 13, a 0, a 6, open circles because there's no equal to bar, and our answer is the numbers between the negative 13 and 6. Questions? Yes. This is an example of the and. Yep. So in our graph, we have the segment with the endpoint. Yeah. Another way of reading it, I said we could read as between. Another way of reading it would be to say that t is bigger than negative 13 and smaller than 6. That it has those 2 criteria. It has to be both of those things. An OR problem is going to look like 2 completely separate inequalities, but it's going to have the word OR between them. So we're going to solve them individually, but we're going to graph them together. So solving the first one, I'm going to subtract 3 from both sides. And then I'm going to divide by 2 on both sides. Since I'm dividing by positive 2, I don't have to worry about any flipping. It doesn't really matter. You can solve either one first. It's all together, no problem. Then I'm going to do the second one. I'm going to add 7 to both sides. And divide by 4 on both sides. Since that's a positive 4 that I'm dividing by, I don't have to worry about flipping. So now I have 2 pieces to my answer. I'm going to put the word or between them, and together those make my answer. So it's telling me 2 different things would work. X could either be smaller than 1, or X could be bigger than 4. And either one of those things would be a good solution for the problem. When we graph that, what that's going to look like is a number line with our key numbers on there again. The first one says X is less than 1, so that's open circle, and less than goes to the left. The second one would be open circle on 4, and greater than goes to the right. So this is where we get our 2 rays with the empty middle. So we could have numbers that are smaller than 1 or bigger than 4 would meet our criteria for our solution. Questions? Okay, so solve the 2 pieces individually, just like examples 1 and 2, but then we're going to put 2 of them together on the same graph. Go ahead and try this last problem. Okay, so 2 separate problems, but put together in one. So for the first one, I'm going to subtract 9 from both sides. And then I'm going to divide by 6. Now this is where some students can make a mistake and say, oh, there's a negative in this problem, I have to flip the sign. It's not just if there's a negative in the problem, but it's if what we're dividing by, what we're doing to both sides, is negative. What we're doing to both sides is a positive 6. So we do not need to flip the sign on this one. On the next one, we add 8 to both sides. And divide by 3 on both sides. For our answer, we put the word or between them, and together they make our answer. Then we put them on the same number line graph. Open circle for no equal to. Less than negative 1 goes to the left. Open circle for no equal to. And greater than goes to the right for the 7. So good solutions would be smaller than negative 1 or bigger than 7. Questions? Your homework is from 1.6 tonight.